Hello everyone. Welcome to my talk on poking Java's backdoor. Start off with, who am I? I'm Nicky Bloor. I'm a managing security consultant at NCC Group. I'm a Next software developer. I've developed software of all kinds, desktop, web games, factories. I like to think of myself as a hacker. I like to pull things apart, reverse engineer, break things, build things, all this kind of stuff. Outside of technology, outside of work and research, I'm a hiker and a rock climber. This photo is me on top of a mountain that's in the middle of one of the biggest military training ranges in the UK. Just over the other side of that fence that you can see, I was told that I risk stepping on an unexploded ordnance. On the internet, I go by the handle NixterDB. So I'm going to start off with a story. All of the research that I tend to do starts off with some interesting job. I came across something new, across something strange, interesting, something that I really wanted looking into a bit more. So I was at a customer site doing a Java application assessment. And this customer, renowned for doing this, didn't provide any credentials until day 3. So I had a lot of time to mess about with things. The supporting infrastructure for this application was included in the scope. So in those 3 days, I did a lot of the usual stuff that you would do. I did mapping of the back-end services. I poked around with the login form of the application, decompiled it, all this kind of stuff. But while I was doing this, there was this one network service that really stood out, and that was this, RMI Registry, Java RMI, port 1099 TCP. I'd never seen that before, but it turns out that was Java Remote Method Invocation. Lots of people had heard of this, told me this is really old stuff, really lame, but that sounded interesting to me. Remote Method Invocation. And this service actually gave me that server before I got the credentials to the application. And it was really easy, actually. It was these 3 lines of Java code. First one, I get a reference to the RMI Registry Service, pointing at the target server and port. I then asked that service to give me an object which was called File Browser. I then said, File Browser, write this file to this file name, and these are the contents. And that got me that and a combination of a few other bits and pieces, but that got me the server before I got application credentials. And now, I couldn't believe just how easy that was. But at the same time, that left me really intrigued, and I wondered how common is RMI, and how often do people use it so insecurely, and also what else can we do with it? So that's how I started off with the work that I'm going to talk to you about today. So I'm going to start off with a brief introduction to RMI for anyone that's not familiar. Like I say, it's Remote Method Invocation, essentially RPC for Java. RMI allows us to execute methods, execute functions that exist within another Java virtual machine. And that other Java virtual machine can be either local on the same system or remote on a completely different host, even somewhere else on the internet. It's very simple to implement, which I think is part of the problem. So RMI itself takes care of all of the connection, the transport of these remote method invocations. In fact, the developer who's using RMI doesn't even need to be aware that they are using RMI. Something that's important to note here is that RMI doesn't mean remote code execution. It's not arbitrary remote code execution. All we're doing is we're asking the server to execute code that it already is aware of, that it already has access to. It looks something like this. We've got 2 Java virtual machines. On the left, we've got a client application. On the right, we've got a server application. When you call a method, a remote method, from the client application, it goes off to the RMI subsystem. That wraps it up in a packet, sends it over the network to the remote JVM. That decodes the packet, sends it to finds the the object and the method to call, calls that method, gets the return value, and does the same in the reverse. Now, all of this is entirely transparent, and to a developer, it just looks like that. We've got an object, ifoo, and we're calling the method bar. The RMI Registry Service is nothing but a directory of Java objects. It maps Java objects to names. So a server application will say, I've got this object, I want to call it this. There you go. The registry service listens on TCP port 1099 by default. And we interact with this service using the java.rmi.registry class. And that's got a series of methods that allow us to do things like bind an object. So we supply a name and an object. You might notice that the type of the second parameter is not object, it's remote. In order to expose an object over RMI, the class of that object needs to implement java.rmi.remote, which is an interface. We can also get a list of objects that are registered with a given RMI registry. And we can look objects up by name. We can also rebind and unbind objects. So an object's been bound, we can say, actually, bind this other object to this name, or we can unbind an object. When I first came across this, when I first looked into this, I thought, oh, it sounds like a free man in the middle or a free denial of service. What if we get a list of all of the objects and we unbind them? Or we get an object, we rebind it so that it points at ourselves and we forward the data on, man in the middle in it. RMI has a security feature that prevents bind, rebind, and unbind from being called from non-local host. And it does that by, when these method calls are invoked, RMI will attempt to bind to a port on the address that request comes in from. So if it's a local address, RMI should be able to bind to a port on that address. If it can't, then it rejects the request. So we can't do those things over the internet, for example. Implementing RMI, like I say, it's really easy to do. So on the server side, we have a class that we want to expose over RMI. And we just have that class implement the interface java.rmi.remote. We create an object of that class, and we bind it to the registry using the bind method. On the client side, we look up the object from the RMI registry, and we use it as normal. So what's the problem with all of this? This is a fairly reasonable sounding method from if this was on the server side of an application. Obviously, you'd have to look into the method calls that this makes to say whether it's secure or not, but we've got a read file method that accepts a username, a password, and a file name. It gets this file manager object. It then calls the authenticate user method to check if that username and password are a valid user. If that returns true, then it returns the result of the read file method for that file name. If this application object factory actually returns a remote object, then the security of that code changes quite significantly. So it looks like this in a successful case. The client will say, we'll call authenticate user, send the username and password to the server. That returns true. The client then goes read file name, sends that to the server returns the file contents. So why don't we just do this? And that's essentially what I did in this. The first time that I came across RMI, that's exactly what I did. So I looked at what security controls RMI actually has, and it doesn't. Except we can sort of argue that we've got access controls because you can't bind, unbind, and rebind from a remote host, but actually not really. There's an issue where RMI would, it does the checks the wrong way around, so it doesn't check that, it will deserialize an object before it checks that the request came from localhost. So the access control happens the wrong way around. I should also elaborate there on encryption. You can have your RMI registry reference use an SSL socket factory. So you can pipe RMI down an SSL encrypted tunnel. I've not actively looked for people doing that, but I've also never seen anyone doing that. I've seen lots of these services exposed to the internet and all over the place. So that's a fairly accurate picture of RMI security. But this is a bit unfair, to be honest. The RMI protocol was designed and created to facilitate remotely invoking methods. It was created purely to do that. And we can liken this to HTTP. HTTP was put together, it was designed to facilitate sharing of textual information. All of the security features that we have in HTTP have kind of been tacked on to the original protocol, and it's evolved over time. And that's largely down to the maturity and how much we use that protocol. RMI is very different in that sense. And so if you want to do things like authentication, proper session management, access controls, you need to build all this into your application yourself. When it comes to HTTP, even if a developer isn't security aware, most application frameworks and application servers actually bake in a lot of security controls by default, and you don't need to be particularly security aware to write a reasonably secure application these days. It's not the case with RMI. So I wanted to look into this insecure use of RMI. Like I say, it's not a secure protocol. In my original attack, I ignored the authenticate method. The actual application, if I tested that during that original attack, the login screen would have called the authenticate method and then just done the other stuff once I'd logged in. But like I said, I didn't need to do that. I bypassed the authentication, essentially, and called read file, write file, execute query, list files, all these kind of methods directly. So I wondered, like I say, how often is RMI used just this insecurely? So the first step in doing this, in finding this out, was to identify software that uses RMI. I tried a bit of Google searching and searching GitHub to try and find projects, but I didn't really have much success. So I wondered whether I would be able to remotely identify RMI software. Now, during one of my tests that I'd done whilst playing around with this kind of stuff, I'd got some exceptions back like this. And the key thing to note there is that the exception that had been fired as a result of me trying to look up a remote object was a class not found exception telling me the fully qualified class name of the remote object. So fully qualified class names include namespaces or package names, and they usually start off with a vendor name, and often somewhere in there there's also the name of the actual application package. So I figured I can probably find these and do an internet search for fully qualified class names, use that to identify some software, start digging around, see what we see. But that exception also told me that the fully qualified class name must be coming back over the network. So I did a bit of digging into that, and that's an example of some RMI traffic. You can see fully qualified class name at the top, rmi.demo.shared, so on. And down at the bottom, you can see an IP address, 192.168.228, and so on, which is actually where that object lives, and where you can communicate directly with that object and invoke methods. And I end up spending a fair bit of time in all these kind of tools, packet captures, hex editors, text editors, Python shells, decoding and messing about with these packets. And along the way, I put together code that would parse and extract the interesting information from these packets. And this information, things like the host and port where an object lives, Java doesn't give you direct access to that information. You could probably get it through some horrible hack, but I was finding it, I was having a much easier time just looking at the packets and extracting the data and decoding those. And that work turned into a tool that I called BaRMIe. And originally, it was just doing enumeration. And this was to support me doing a bit of research into what's out there. BaRMIe does proxy-based enumeration of RMI registries. So we start a server socket that listens locally, and instead of creating a RMI registry object that points at the actual target, we point it at this local server socket, which then directly connects onto the target. The traffic for that connection then passes through our proxy, and we can see what's going back and forth. We then get a list of objects that are exposed through that registry, and we start requesting them one by one. When the data comes back from those requests, sometimes there was quite a lot of data that came back for a single object, so we buffer that data that comes back. And when the call to registry.lookup returns, we grab that data, everything that's in the buffer, and we parse that and extract useful data. So the class names of the remote object, the IP address where it sits. And I use this to do some knocking on Java's back door. I use this to find RMI software that was sitting on the internet. So at the time, I found over 14,000 RMI services on Shodan. So only a few. And between those services, I found over 27,000 Java objects that were exposed. Not all of those were exposed externally. So we've got some guy here that was learning RMI, and the objects were listening on localhost. A lot of these probably shouldn't be exposed. So I've got some examples here. Vehicle search service, driving license manager, camera captured images, CC payment service, root terminal, admin API, system, chain gun API, that sounds fun. Beer machine API, Alva Porter, and praise service. And the point here is that, so I don't know what any of these do. I didn't find a lot of the software that I went out looking for. But the point is, this is the kind of stuff that people expose to the internet over RMI, even today when RMI is considered old and nobody uses it anymore. And when we go back to that first example, if they're using RMI in that kind of way, this is pretty bad, right? So I picked out some examples that were fairly common amongst my results. First one, Apache JMeter. I have no idea what it does, but this is a class name that was exposed. It's open source, so you can download the sources, and you can review the remote classes and methods. So any class that implements java.rmi.remote, that can be exposed over the RMI, through an RMI registry. So the methods of that class, the public methods of that class can be called remotely. So this is a list of methods that we've got, and the ones that stood out to me, it looks like anybody can configure that service or set the properties. Again, I have no idea what JMeter does, but it's another example of insecure use of RMI. Another one, Temis Remote Admin Server. Again, that's a class name that was exposed. Sounded interesting, so I had a look, and I couldn't find source code, I couldn't find the client jars, server jars, I couldn't find anything to do with this, in fact. But BaRMIe actually revealed an interesting annotation. So the classes could have string annotations. In this case, we've got a HTTP URL that ends in admin_client.jar. I was actually able to go to that URL and download this jar file. So I did the same thing. I decompiled it, looked at the code, looked at the remote objects, looked at the methods, and I've got some examples. So first thing that I saw was they've got an authenticate method. It takes a string and a string, probably a username and password, and it returns a user profile object. So what they should be doing is using this user profile object to then authenticate subsequent requests, like a session ID, like in HTTP, a cookie, if you like. But then I saw this. Anyone can configure this remote admin server. And then you can get the admin key, whatever that is. Add a user, if you can guess the 4 string parameters. There was a possible account takeover. You could get a list of all users, which returned a list of user profile objects. You could then pass a user profile and a string, probably a new password, to the change password method. Or you could just say user profile.getPassword and get that user's password. Some more remote methods. Get the database configuration there, standard stuff, but username and password for the database, okay. So what's the problem with RMI? Well, we've kind of got this. We've got all these authenticate methods, but we just walk around. But it actually gets worse than that. So deserialization. Hands up if you are familiar with deserialization attacks, Java deserialization attacks. Okay, that's good. So deserialization is the process of converting data into runtime objects. It's often implemented or used insecurely. Generally, deserializing untrusted data is bad. And RMI actually is heavily dependent on Java serialization. And I discovered this while I was working through packet captures and hex editors and decoding this traffic. So what I actually ended up doing there was writing some code that sort of decodes a serialization stream and prints it out in a nicer format that you can read. So the most commonly exposed RMI service that I saw on the internet while I was doing these scans was Adobe ColdFusion, which exposes a class ColdFusion.flex.RMI data services CF proxy server stub. And I installed ColdFusion in a VM, I had a look around, I decompiled the jars, and I didn't find any like really interesting remote methods, not like the other targets I looked at where I had authenticate, I had read filed and all this kind of stuff. But then I noticed this. Now those that are familiar with deserialization attacks should notice the issue there. We can pass any object we like as a parameter to this method. In either of the last 2 parameters, one's an array of objects, one's a map which can contain arbitrary objects. So yeah, we call this fill method, and we can have the server deserialize any object we want. So I've got a little demo of this. So far, I'm on 0% success rate with live demos, but we'll see. Okay, up. So we have ColdFusion's admin interface here. And the only thing that I've changed from a default install is I've enabled Flex integration. Doing that enables this ColdFusion RMI service. Apart from that, this is default install and was fully up to date on Monday. Tuesday first thing, so like just after midnight. So, Process Explorer, somewhere up here we should find ColdFusion.exe. Drag this over. And now we have Notepad. Properties of that, we can see the command line that I passed in, 44con 2017, and that's running as system. But it gets worse than that. And this is where I stumbled across something that I'm calling Java's backdoor. And I stumbled across this. I was testing some code. And along the way, I realized, oh, I didn't mean to do that. I'd done that bit wrong. But that code still worked. And I had to retest this like 50 times because I couldn't believe it worked. So what was that code that I was testing? I wanted to create a full RMI proxy. So with my previous work on BaRMIe, I was successfully proxying RMI Registry connections. So you first go off to that registry, you ask it for an object, the object comes back, and that object actually listens on a different address. So yeah, the RMI registry doesn't handle the actual method invocations. So I wanted those method invocations to go through my proxy so that I could, for example, fuzz the protocol, or even extract data, whatever. I just wanted to play around with the traffic. Like I said, the invocation's handled by the actual remote objects rather than the registry service, which can sit on a different port that's potentially on a different host. So I built a proxy to man-in-the-middle remote method invocations, and it was a bit fiddly to do. It was a bit of a nightmare to put together and get working nicely. So I've got a horrible diagram that explains what this code did. It started off with, so we've got an RMI client application on the left, remote RMI registry on the right, and then below that, remote RMI object. The first thing it does is we create a registry proxy, which is configured to directly connect to the RMI registry. We have our RMI client connected to the registry proxy. We then request a remote object through that registry proxy, which forwards the request on directly to the RMI registry, which then returns the object to the proxy. At that point, we intercept the object, we decode the contents of the packet, and we start up an object proxy. And we configure this object proxy to connect to the real RMI object. We then modify the packet that came back from the registry before we send it back to the RMI client, and the modified packet points at the object proxy on localhost on whatever port that's on. When the RMI client then invokes a remote method, that hits the object proxy, which forwards the data onto the RMI object, and we're in the middle of the connection. That is far easier to explain than actually doing it, but that was what I was working on. And one of the things that I wanted to do, like I say, was a bit of fuzzing and things like network level payload injection. So rather than actually having that interface from ColdFusion and invoking the method directly through Java code, I just wanted to sit on the network and go, there's the payload. You shove it in the packet as it's traversing the network. And what I accidentally ended up doing was, in my RMI client code, I called a remote method that had a string as a parameter, rather than a method that had an object type parameter. Just while I was fiddling about with things, I'd left the wrong piece of code uncommented, and that happened. And so this proxy replaced the parameter to the method that accepted a string. And I was playing around with some of the YSOL serial payloads. So next thing, I've got calculators. I'm like, how the hell did that happen? What's going on? So just to have a quick look at what was actually going on here. When we remotely invoke, say, a print string method, we've got a string parameter. You see it's 10 of the letter A. So that's what it actually looks like when it goes over the network. And that's entirely serialization data, apart from the first byte, which is an RMI packet type byte. But this part is the actual parameter to the method. 7.4 tells us it's a string. The hex 000A tells us that the string is 10 bytes long, or 10 characters long. And then the 4 ones are the actual string contents. Now, if we serialize a dummy object for this, just for the example, because the actual payload was like, huge, we might get something like this. And in this case, this is a dummy class that had no properties. It was minimal class. Serialized, we have something like this. And the interesting part is the highlighted bit, because that's the actual object description, class description, and the details to recreate that object, to deserialize that object. The first 4 bytes are just the Java serialization header. So what my proxy had actually done was this. You can see that's not the string parameter, but an object, which, like I say, was actually a YSOL serial payload. So what I've done here is remotely invoked an illegal method call. I've called print string, which accepts a string parameter, and I've passed it a new object of type dummy, which isn't type compatible with string. You cannot run that Java code, you can't compile it. It's an illegal method call. So this caused the server-side exception because, like I said, dummy is not compatible with java.lang.string. So when RMI receives this request, this method invocation, it deserializes the parameter, tries to then assign that to the method call parameter. That fails, so you get an exception back. But by this point, the payload has already been deserialized. And so those that know about Java's deserialization vulnerabilities and exploits know that that's the point where the vulnerability is, that's when the payload is executed. So that's why I ended up with calculators popping, because the YSOL serial payloads, when they're deserialized, what they do is execute an arbitrary command, in this case, using the classic calc. So essentially, if we can call a remote method that's exposed over RMI, at the network level, we can replace the method parameter with any object we want, any YSOL serial payload, any deserialization payload. That will be received by the server, deserialized, and executed. There's a slight caveat to that, which is that the parameter that we replace, the method parameter we replace, cannot be a primitive type. So it can't be an int, a long, Boolean, and so on. It can be an int array. It can be a integer, which is the object that wraps the int type. It can be an array list. It can be any other class of object. And that's just to do with the serialization protocol and how that wraps that data up. So back to BaRMIe. Over time, I have written code that attacks various different RMI services using both legitimate but dangerous methods, so things like write file without authenticating, and also proxy-based attacks that introduce further risk by, we just modify the parameter, we swap it out for a dangerous payload. Unfortunately, all of these attacks require knowledge of the remote classes and the method signatures. Anyone familiar with RMI and vulnerabilities and attacks, you might be aware of some work by a guy called Adam Bolton in 2008. And he looked at, I ended up doing some similar work, not being aware of that, but he looked at whether you can sort of do a zero knowledge attack against RMI. And what it comes down to is when you actually invoke a remote method over RMI, Java generates a hash, which is based on the method signature. It's based on the method name, the return type, the number and types of the parameters. And it generates this hash. It actually does a lot of things that reduce the entropy of that hash. So it's a 64-bit value, but the entropy is a bit less. So there's a bit less to brute force if you wanted to do that. But you had to brute force this hash in order to invoke a remote method. The interesting thing about Adam's work was that he actually took it a step further and he went, well, let's say that I did brute force 9 quintillion values over the network to come up with a method hash. What happens if I send a method hash and then I don't know what the parameters and return type of this remote method are? What happens? And it turns out Java actually is really helpful and sends some nice exceptions back which allow you to work out what the types of the parameters are. So you can perform a zero knowledge attack, but you need to do some serious brute forcing. So I ended up, so I've got this enumeration functionality that was already in BaRMIe. What I'm doing at the minute is incorporating all of these different attacks and payloads that I've built up into one single tool to attack RMI services. The idea is, once I've got details of a class and I know that there's some dangerous method, like write file, for example, I can basically create an interface that has that write file method, request a remote object of that class, cast it to that interface, and then call the write file method. Like I say, without calling this authenticate method if there is one. So we can enumerate remote classes, so we can find which attacks we can perform, if you like, which methods we can call. And we can also, where there aren't dangerous methods, so like in the ColdFusion example, we can look at whether the application uses any Java libraries that would enable us to perform a deserialization attack. And so, like I said, I'm building all this code into a single tool that will perform these attacks, and you'll be able to essentially run it against an RMI service. If it's got a known class, then you can attack it. That's what BaRMIe is becoming. I'm having to do a bit of I'm going to be releasing this in the next week. It's going to be missing certain attacks because I'm going through responsible disclosure. I'm also re-architecting it at the minute as well because the code base is horrendous. I've built this up from, there's been an attack against that, some proxies. And so I'm re-architecting it and turning it into something that's easily extendable. And like I say, I'm going to be releasing this in the next week. So keep an eye out on my Twitter if you're interested in this. I'll be posting it on there, my blog and my GitHub. I've got the details later on. So that's actually that. There's more that I would have liked to have included, but it kind of ended up being, I'd end up going down this big rabbit hole and not having the time to talk about this. So I'm actually going to write a blog post with some more of the details on this. But just a brief conclusion, RMI lacks maturity. It's not as well used as other protocols like HTTP. And it's often used very insecurely. It's very easy to implement stuff using RMI, so people just, and it's also very transparent, so people just use it. they don't need to think about authentication. They've never had to do that before, so why would they do it now? Object injection attacks are almost always possible because we can replace the method parameters on the wire. Old and interesting technology can actually be fun and fruitful research target. In terms of this object injection thing, I just wanted to mention something, because I reported this issue to Oracle. I reported a couple of issues to Oracle, actually. And there's a Java enhancement proposal, I think it's JEP 290, which in newer versions of Java allows you to configure a global deserialization filter. And the idea behind that is you can whitelist classes that can be deserialized. So if you have a method that you're exposing over RMI that you know accepts a string parameter, you can whitelist java.lang.string. Then if I was to perform this attack against your application and use a proxy to replace the parameter with some other object that would potentially execute commands on your server, Java would kick in and go, hang on, that class isn't actually whitelisted, we can't deserialize that. So there is actually a fix, but Oracle are putting the onus on developers, and really I think that it should be Oracle's and Java's problem, really. Why would you deserialize a hash set when the parameter type is string and hash set isn't compatible with string? But that's what they're doing, and like I say, they're leaving the onus on the developers to fix this. But yeah, that's that. There's where you can find me. Thanks for coming. Hope it's been interesting. Any questions?